This is Neutral Atom Lattices, a scalable quantum information processing architecture by Sebastian Peralta. Motivation and potential impacts. So here are some neutral atom lattice favorable qualities. As of 2016, they demonstrated the most qubits in the same system, which is 50. Thousands of these atoms can be optically trapped near each other without affecting each other's quantum states unless called upon to do so. There is a favorable density, addressability, and because of close proximity is ready for entanglement. There's a weak, well understood interaction with the environment, and states can be precisely measured via fluorescence. Also, there's long decoherence times, on the order of several seconds if desired. Yeah, as I said before, is arbitrarily dense networks, and yeah, it's a robust qubit trap. So the impact of this is it's an important step towards a scalable quantum computer. Currently, like the state of the art is at this addressing stage, so no like multi-qubit gates or error correction. But in addition to quantum computation, there's a broad range of benefits. Since they're neutral atoms, that has links with metrology, and there's also links with timekeeping. Also, these high precision control, initialization, and probe techniques will definitely like better the experimental study of quantum mechanics and how it borders with classical mechanics. So here's some competing schemes. Okay, for trapped ions, uh, the architectures would operate in a similar temperature regime. One of them is ion shuttling, which is complicated and hard to access the qubits. Another is microtrap array, and this is better than ion shuffling, but you're still limited to 100 micrometer spacing, which is a lot more than 5 micrometers in the neutral atom lattice. For a superconducting qubit, you have circuitry elements that limit the density, and you have a common data bus that makes it really complex and hard to access. And there's feedback latency in the current controlling schemes, or the current carrying control stuff, and that inevitably introduces heat. So if you want to bypass that, you could use a microwave cavity mode instead, but that makes a large volume per qubit. And for solid state scalable architecture, you can use magnetic dipole interactions for coherent coupling between NV centers. And it's room temperature operation, but the individual addressing of spin states are difficult. So a little history. So this all started with the development of cooling techniques in the 80s and 90s. First paper to propose quantum logic gates and optical lattices was in 1998. They control NOT gates, although they didn't mention the fidelity. They said they needed to figure out addressability. Then there was 3D projection sideband cooling in 2012. 2004 and 2011, they did 1D and 2D addressing and eigenstate flipping, although it was very sparse and didn't have to worry about nearby atoms accumulating phase or anything. And then finally in 2015, they did addressing and gate demonstrations on a 3D lattice. This time they did have to worry about crosstalk, which is accumulating phase and unwanted non-targeted atoms. And in 2016, the same guy really improved upon his scheme in 2015. He improved on addressing, crosstalk, and gate fidelities. How does it work though? So the apparatus setup is a lattice made from 3 interfering pairs of blue detuned laser beams, and their incident angles are 10 degrees. It makes the fringe pattern in C, and the effective lattice you can use is B. The authors were interested in a 5 by 5 by 5 subset of this, and they're spaced by 5 micrometers, a lot smaller than 100 micrometers in the ion traps. And the main 2 papers used carbon atoms as their qubit. The way they started it out is they would cool as many as they could down to the ground vibrational state occupancy, and they would microwave transfer to the qubit basis. After that, they would clear atoms in one of the storage bases. So in this paper, in the 2015 paper, they did 3, 0, and 4, 0. Those were the quantum numbers for the 2 bases. So they cleared all the 4, 0 states, and they were just left with 3, 0. This resulted in just a 40% lattice site occupancy. And this is not only just because they clear the 4-0 states, it's also because the cooling results in light emission, which would knock atoms out of their lattice sites. So how do you address these? You have two circularly polarized addressing beams, and their intersection is the atom that you want to target. This results in star shifts among a bunch of atoms, but the targeted atom will have a star shift 2 times greater than the other ones. The star shift is just the electrical field analog to the Zeeman shift. And you can change these addressing beams with faster than 5 microseconds with microelectromechanical mirrors. And the coherence time is on the order of several seconds. Okay, so when you have the targeted atom that has been star shifted, which is basically the electric field version of Zeeman shift, when you have it star shifted, you can apply an omega 1 microwave pulse to get it from the storage base, which is the omega naught bandgap that you see, into the computational base, which is the omega 1. And once you're there, you can apply an arbitrary microwave pulse, omega 2, to do a Bloch sphere rotation. On the right, you can see the pulses where it says microwave. There's the black pulses are omega naught. So a lot of those, because every time you address a target, you end up getting unwanted noise and phase accumulation of the non-targeted bits. So you make sure that you get this accumulation twice, and then you do a pi pulse in between to flip the states. That way you kind of cancel the accumulation. And this is done through the dummy gates, I guess. As you can see next to plane 1 and plane 3, there's 4 stages, and only 2 of them they're actually addressing a qubit. For some reason they like to address 2 qubits at once and do gate operations on them. But the other 2, those are the dummy ones. Yeah, so the gate fidelities for the 1, 2, and 3 rotations you see there are 0.95, 0.91, 0.93, and the change in identity fidelity for the neighbor atoms are all lower than 0.003, which is pretty good. Okay, so this is a 2016 paper, which is a very, very similar setup. Here, I just want to tell you what target, line, and spectator atoms are. Target is the atom you're targeting. Line is if you're in line with one of the addressing beams. And spectator are all the other atoms. So here you don't want a star shift that is 2 times as big like you did in the other paper. What you want is a vector light shift. And you want to make sure that, so if you look at graph A, you choose a star shift F, which is, and that blue curve or that purple curve is for the line atoms, and you want there to be a region between that peak and the green target atom peak, so that you can get a microwave pulse, an optimal one of delta naught, which is you can see in B, so that you're not in any of the resonances, and you're not going to have a transition into a different bases. And so this delta naught, that's your detuning of your addressing microwave pulse from the spectator resonance. Okay, so you're not on resonance. And the cool thing about this is that your addressing pulse is your gate. You don't need to go from the storage to a computational basis. You just stay in your basis, and you have your gate, which is a phase shift along the z-axis. Similar to the other paper, you mitigate the accumulated phase of spectator and line atoms using dummy stages and spin echo pulses, which are the black ones in C. And the purple ones in C, that is your addressing pulse. And then you can see plane A and plane B, you see the dummy stages, where they're only addressed twice. And to get an arbitrary like block speed rotation, you can do a global Rx pulse, or Rx pi over 2, Rx negative pi over 2 pulse. And these will cancel out for the spectator ones because they cancel out and they don't feel the Z1 due to the spin echo pulses. The gates here have a lot higher fidelity because they're better because this gate has extreme insensitivity to addressing, beam, alignment, and power, and the storage basis has insensitivity to magnetic fields and vector light shifts. Also, the way they would figure out the errors of the different classes of qubits is they did a randomized benchmarking protocol, which is where they combined computational gates and poly gates and identity gates, followed by a detection gate that would either put the target or the non-target gate into the 1 qubit state. And with this scheme, they could determine the errors of the different qubits. So the spectator error had 7. You can see them right there. They're really close to 10 to the negative 4, which is ideal. They're not quite there. And the reason for this is actually I'm going to discuss on the next slide, because this is the state of the art. Okay. Yep. So the reason the authors didn't think or thought that their errors was not below 10 to the negative 4 is because there's a lot of errors from the microwave power stability and also from the spontaneous light emissions from the addressing light, which is actually the biggest source of decoherence. And I think they can reduce it by a factor of 8 if they double the addressing light wavelength. And if they make the lattices deeper and they use an adiabatic addressing beam turn-on, then it would make the associated heating negligible. So yeah, those are some things to overcome for the state of the art. In addition, they need to be able to fill the vacancy using, and a potential solution is Maxwell's Demon solution. The way they do this, they just determine where the atoms are and they execute a series of reversible operations to move them so that you have a filled sub-lattice. Another thing that they need to do is come up with a 2-qubit gate, and a possible implementation of the Rydberg gate solution. It's where you excite atoms that are nearby to a highly energetic state with the electron really far away from the nucleus. It results in a strong dipole-dipole interaction for quick entanglement, and a Rydberg blockade, which is analogous to the Coulomb blockade. Only one electron can move through a narrow channel. And the good thing is it can entangle nearby bits with just 3 pulse sequence, except the fidelities are only 75%, and it's highly sensitive to background electromagnetic noise, so you'd have to mitigate that a lot more efficiently. And because of this high fidelity was not reached for the 2-qubit gate, then it's not enough to look at error correction. So this is the state of the art, and coherence time is again about 7 seconds, which is pretty cool. Yeah, that's it. Thank you.